So we talked a lot about, the last lecture was focused on the second law of thermodynamics. And that second law, a perspective of the second law is to tell you what you can and can't do with thermodynamic processes. Specifically, we looked at cyclic processes, which we call engines. That's what a cyclic process is. It's just the idea of an engine where heat goes in, work is done, exhaust happens in some form, and that's what we mean when we say engine. Just some series of thermodynamic processes that through work accomplish a task, you know. And we ended up, and by the way, so just to remind you about this, not only did I upload that video from the second part of the chapter 19 lecture, but I also added that extra 10 minutes or so to the last lecture. There was just like a couple examples on a couple slides I weren't able to get to. So I originally uploaded the video of that lecture, and then I re-uploaded the lecture with the added 10 minutes or so. So if you haven't seen that, I'm going to kind of explain things right now anyway. But so, I mean, I actually discussed this in the previous video, but the idea here is we have a reversible heat engine. I'll talk a little bit more about reversible because we talked a bit about that concept before. But a perfectly reversible heat engine where you take some hot reservoir, you do work, you exhaust some of some energy to a cold reservoir. If that work is being done to operate a refrigerator, then the devices are going to cancel themselves out, because as much hot reservoir comes in is what's going to come out. Same thing with the cold reservoir. Ultimately, nothing is really going to be done in this process. If you realistically do what you see here, there will be inefficiency that will take place, and you cannot harness all of, for example, the hot reservoir's heat. You can't harvest all of the cold reservoir compared to what you will expel in the heat engine. So this is something that's not quite doable. So we have another statement of the second law. This is, I don't know how many statements we have. We have a lot of statements which touch on different aspects of what the second law is all about. And so this one here says no heat engine operating between reservoirs at temperature hot and cold, so we call it TH and TC. These are hot and cold reservoirs. Uh-oh. Sorry. Anyway, this was the first. I wasn't sharing my slides. Okay. Yeah, this is the first slide about how you can't have a perfectly reversible heat engine and a perfectly reversible refrigerator work with each other. They'll cancel each other out. And I'm on the slide now. So it says no heat engine operating between reservoirs at TH and TC can be more efficient than a perfectly reversible engine operating between these temperatures. Okay, so that's what we're going to be focused on for a good part of this discussion here, is this particular statement here, what it means to be efficient, what it means to be a perfectly reversible engine. Okay, an engine like this, okay, if this was a very efficient heat engine and a very efficient refrigerator, you really can't improve upon a process we have the most efficient things. If you did, you would have a process like this. And that ultimately is a statement of transferring things from hot to cold spontaneously without any work, and that's something that you can't do. So this statement down here is equivalent to saying that you cannot spontaneously transfer things from cold to hot. And it seems weird because we're talking about something that is seemingly very different, the efficiency of an engine, right? And we've talked about efficiency so far. Efficiencies really had a lot to do with how much of the heat reservoir are we using in a cycle, how much is expelled, how much work is being done. Well, we're going to touch more on the concept of efficiency here and how it relates to reversible engines. Okay. So anyway, so we want to look a little more carefully at the concepts of efficiency. Okay. And the maximum possible efficiency you could have of a heat engine. So remember what the efficiency is of a heat engine is, and I will remind you of this. The efficiency of a heat engine. So for the heat engine, right? Remember it's efficiency is the work divided by QH. So really what this is saying is how much work can you do with the amount of heat you can draw per cycle, okay? And you can't get to 1. The efficiency can't be 1. And what we're saying now is this: not only can the efficiency not be 1, but it actually will be less than or equal to some other quantity here that's not even 1. So we're making a more profound statement here. It's not just that you can't reach 1. No. There actually is a smaller number than 1 that you can't reach. And the same thing for a refrigerator. Remember, the efficiency of the refrigerator is we had to look at the cold reservoir divided by the amount of work that we do. Okay? And we kept this, obviously this is at an absolute value because we want to make sure that we don't have our E negative. It doesn't make any sense. And, this could be very large, but it's not infinite. It's not infinite, okay? Because if it was infinite, you do no work, and then cold is being transferred to hot. But what we're saying here is this: it's not that it's infinite. That's not the perfect one. There is, again, a number here that it is, less than or equal to something. And there's a particular number here that is a limit. It's not infinity. Infinity is impossible, but we could even go lower than that. All right, so let's start looking at that. Okay, we need a perfectly reversible engine. Now, you might remember a little while ago, this would have been at the, what was that actually? Let me think here. This would have been at the, this was last lecture actually, where we talked a little bit about reversible processes. And what I mentioned at the time is that an isothermal process is a reversible process. When something is at the same temperature and it maintains that, then what happens is you can reverse the process. And when we say reversible, let me just be clear what that means. A reversible process is one where the state of the system changes, but the environment stays the same. So you can manipulate your system in such a way that there's no influence on the environment. So in an isothermal process, you can have heat being transferred, but the temperature doesn't change, and that doesn't necessarily change your environment. Now, there happens to be another way that you can do a reversible engine. We really didn't talk about this at the time, but an adiabatic process can be reversible. That's a bit harder to do. Again, to be very clear about what we're talking about here, we're talking about theoreticals. We're talking about approaching theoretical limits here. But having a process that is truly isothermal and truly adiabatic is impractical. It's like saying having a frictionless surface. You can get close to that, right? But you ultimately cannot achieve it. So our reversible processes are going to come in 2 forms here. An adiabatic process, where there is no energy loss at all. So there can't be any friction or dissipation in any way, maybe through light, sound, whatever. And also an isothermal process, where you can transfer heat, but it doesn't change the energy, the internal energy of the system. And any engine that uses these 2 processes, okay, is what's called a Carnot engine. Okay, named after, I don't know, James Carnot. I actually have no idea what. Gregor. I'm pretty sure his name is Gregor Carnot. Am I wrong about that? Gregor? Leonard Carnot. I was close. Not really. Not close at all, but anyway. All right, Leonard Carnot. Yeah, he developed this theoretical idea of the most efficient engine you could possibly have. And we today call it a Carnot engine. It is a perfectly reversible engine. It's a cyclic process. By the way, just to be clear, engines are always cyclic processes. You go from one state and you go around on a PV diagram back to original state. And it has the maximum possible thermal efficiency you can have because all the processes are reversible, meaning they're at its essence, there is no loss that happens. You know, a lot of times when you have processes that are not as efficient as they could be, it's because there's energy loss through various things. One of them, say for example, is friction or excessive sound or vibration or whatever. And so what we want to do is this. We want to make comparisons. The reason why you're going to learn about the Carnot engine is you're going to learn what the laws of thermodynamics allow you to do. What's the best thing that you can do with the laws of thermodynamics? And that's what the Carnot engine is. Okay. So while this is a fancy term, Carnot engine, you should translate that to be the best that one can do. Okay, so buckle up, right? Here we go. This is our basic Carnot cycle, okay? Step one, we start at point A up here. And in step one, we have a isothermal expansion. Now, if we're going to expand the working substance here, we're going to have to input heat in order to make sure that things stay as constant temperature. So we go from point A down to point B. We have the addition of heat, but we stay at the same temperature. Okay. Now, work has to be done here. Because remember, if you have an isothermal expansion, what that means is that your delta E thermal is 0. I don't know. I'm learning this thing here, just to let you know. So occasionally it does this thing where it just does a dash across. I don't know why it does that. I'm doing something wrong. I haven't learned how this works. So please, I apologize if it looks like I'm, writing like a first grader. I mean, my handwriting is bad anyway, but whatever. All right, so that's the first step, isothermal expansion. And that's a reversible process because if we kept at the same temperature, we could extract out heat, lower the volume, and everything would be the same. Okay, so if we go from B to C, that is going to be an adiabatic expansion. So the volume continues to expand, and there is still work being done here, but Q is 0 here. And if Q is 0, that means E thermal, right, is equal to the work that's being done, right? And we're still expanding here, so our volume is still going up, but there's no heat in or out, right? So there's additional expansion there. Once we get to C, we're going to go through basically the opposite process now. We're going to have a compression, first an isothermal compression, and that's what heat will be drawn out as the volume goes down. And that's what our QC is going to be. And then when we get up to part 4 here, when we go from D to A, we have an adiabatic compression where, again, Q is 0 in that process there. The work is negative, and we're brought back to the original state. Because every segment is either isothermal or adiabatic, it's considered to be a reversible process, and it will be as efficient as you possibly could have with the laws of thermodynamics as we know it. As we know it. Okay, so let me go on a bit more about this stuff here. Okay. So those are the steps. Okay, the gas expands isothermally at temperature TH, absorbing heat H. Now, to be clear, what happens here is the following. Our QH is equal to the work being done. Now, the work being done in an isothermal expansion, remember, the work is the integral of P dV. For P, we substitute that with the ideal gas law, so it looks like N R T, right, over V dV. And that just has us end up with N R. Now this T, I'm going to label TH. And then this is going to be the natural log of, you know, the final. It's going to be the final minus the initial. So this is going to be like VB over VA, for example. Okay, sorry, that didn't look. How do I make this? See, I don't know how to make it thinner. I'll figure this out eventually. All right. So now, when it expands adiabatically, we end up with an adiabatic relationship. So you might remember that the adiabatic relationship looked like this. TC, volume gamma minus 1, and TH, volume, I'm at the edge there. Okay, so this is also a gamma minus 1 up here too for the exponent. Okay, and then when we get down to the other two, it's the same statements. Same statements, okay, isothermal, so it's going to be N R T C, and then this is going to be the ln of the volumes, and the volume again is final minus initial. So if we go back here, in the isothermal process, this is going to be final minus initial, so it's going to be D over C in this process here. So you can put that as, where did my stuff go? This would be D over C. Okay, for the adiabatic process, by the way, that would have been, B to C. So we went from hot to cold. So this would have been C, and this would have been B. B and A, B, C, D in the process there. So there's subscripts for C and H, hot and cold, but for the volumes, it's A, B, C, D, depending on where you are there. Well, down here you have a similar thing. You can say that, okay, well, I have my hot reservoir, and that's going to be at a volume of A. And you have your cold reservoir, and your volume is at whatever it is at D. Sorry, it's a D. All right, so that's how we would express thermodynamically everything going on here. The Q is given by the nRTH times the logarithm of the volumes. We have the adiabatic process. And so when you combine all this stuff together, you get a really interesting relationship. So it's a lot of substitution. What you would have to do is you substitute, you take a ratio of H to C here, and that matches this ratio here. But what you would find is that the Q, the volumes that are up in here, the ratio of these volumes end up being the same, yada, yada, yada. There's a lot of derivation here, which I don't want to go too heavily into right now. But we end up with this really beautiful relationship, and it's this. When all is said and done, so what you can do is you can take a ratio of this QC to QH, and then with the volumes that are in here, you can create a bunch of relationships with temperature. Those end up canceling all out, and you end up that the ratio of QC to QH is TC to TH. And this is really cool because our perfectly reversible cycle here can equate the heat and going in and out with the temperature going in and out. So back over here, our efficiency now, this is the same statements as before because our old efficiency was this. Our old efficiency was this. Q, well, that was actually W, right? It was W over QH. Well, that actually is QH minus QC over QH. And then we created this ratio here, QC over QH. But now that we have this new relationship, we can replace everything with temperatures. So that's cool. That is very cool. I remember when I took this class and I saw that, I was like, you know what? Thank you, Carnot. I don't remember what your name was back then, and apparently the name is Leonard. But at the time, I thought Carnot was a pretty cool dude. Pretty cool dude, because this is more practical now, right? This is about what temperature you operate in. Because the heat is more abstract, to be honest, right? The heat is, it's whatever you can extract out. Maybe it has to do with specific heats or other things. But now this is about temperatures. And so if you have a process, for example, a heat engine, okay? Like right now, okay, my air conditioner's going off, right? And where's this heat coming from? Well, it's coming from inside my house here, right? So it's whatever the temperature in my house is. I leave my thermostat at 80. I'm a maniac because I don't want to pay $1 million of my energy bill. So I keep my thermostat at 80. So that's my QH. Now, when the air gets pumped out, I don't know what it is. I can go grab my thermometer and test it, but I can test what that is coming out, and then I can get an efficiency out of that. I can actually calculate what my air conditioner could do if I created it as a Carnot engine. Now, the reality is I can go check out my energy meter over there, and I can figure out what I'm really doing, and I'm probably nowhere close to the Carnot engine, but at least I will know how good I could be with that process. So that's the idea. Okay, anyway, I just want to emphasize one thing here, that's this relationship. The maximum efficiency engine has this absolutely wonderful proportion. We can relate the heats going in and out to the temperatures of the reservoirs. And that is way more useful, way more practical stuff. Okay, I know there was a lot there. So when it comes down to efficiency, right? When it comes down to efficiency, again, you have this statement here, 1 minus Tc over Th. So if you take any thermodynamic process and you can ask yourself, well, this is the best that I can do with these temperatures. How can I do things better? Well, it all has to do with this ratio here. If you can have a process where your Tc is very low and your Th is very high, you can improve the efficiency of that process because now it's a new process. So something like a jet engine, for example, that they're shown in this picture here. This looks like something out of Half-Life, to be honest. Like, I expect to see that in Black Mesa. Anyway, that looks cool as hell. I don't know who's testing out something there, but that looks like a barrel of fun, honestly. But the heat engine here, this has an enormous efficiency. Why? Because your hot reservoir, which is done through the the temperature of the intake here, is enormous. It's very high. You're typically doing some kind of combustion of fuel that's being expelled out of the back. If that's the propulsion being done here, a lot of jets work that way. And then what's your TC? Your TC is whatever the exhaust temperature is, which is going to be a lot lower. And so jet engines are very efficient because they have such a dramatic difference in their reservoir temperatures. And the more you can do that, the greater efficiency you can have in your engine here. Of course, there is limits to this, right? You can't heat up something as high as you'd like, and you can't cool things as low as you want because, well, you could have phase transitions, you have strength of materials, you have all kinds of things you got to worry about. Ooh. This is all engineering stuff here. This is where it gets interesting, right? This is where you start delving into this stuff. Can I push the limits here? Start looking at your materials. Start saying, what can I withstand here? You look at repeated uses. You look, I don't know. Now it sounds interesting. I really hated engineering when I went to school. I took a bunch of engineering classes and I was just like, this is lame. But now that I'm talking about it, it sounds like fun. It's probably awful, though. All right. Anyway, so the statement here is this. No heat engine, or no engine, period, actually, can be more efficient than a Carnot engine operating between the two same temperatures. That's the key. That's what we're talking about here. And so we're going to start making a lot of comparisons with the Ideal Carnot engine. That's the idea. showed this picture before. You know, if you had an engine that was very, very efficient, then it could be used in conjunction with the refrigerator. And the idea is that whatever's going in here eventually is going to come out. And any, you know, and any, any extra heat you have here will eventually be taken out with the work that's being done. And so if you reduce this down, you end up having a statement like this. And, you know, the QHs drop out here, the QCs drop out. Any delta going in here is eventually going to be the work that's being done, and you just can't do it. You just can't do it. So, all right. So, question for you here. Let me know what you think in the chat. The efficiency of this Carnot heat engine is what? What's the efficiency of this engine? It's not B. Why is it not B? Someone tell me. Barton. Man, why is it not B? Kelvins is right. Kelvins. Yeah, you got to do things in kelvins, right? You got to do things in kelvins, right? So if you convert these to kelvins, this is 473 and this is 673, and you take that ratio, you're closer to, yeah, you're closer to what? What are you actually going to be there? Was it going to be like around 0.3 or something, right? What is that? 0.3. I'm going to say it's 0.28. That's what I'm going to say. I have no idea what it is. I'm going with 0.28 because intuitively the numbers seem like 0.28 to me. It's 0.3. 0.3. Oh, well. Okay. Yeah, it was 0.3. Okay. 30% efficiency. That's it. That's all you can do with this engine. You cannot be better than 30% efficiency. That's crazy, right? You take energy out of this hot reservoir, and, you know, the best thing you can do here, right, is take out 30% of the energy and do something with it. And 70% by the laws of thermodynamics has got to be tossed. All right. So that's rough, man. Now, let's do better though, right? How we do better? We up the hot reservoir, or we lower the cold one. It's probably easier to up the hot one. And if you up the hot one, you can do better. Yeah, so, all right. The efficiency of this Carnot heat engine is what? This is different. I got the kelvins in here now. So let it rain B's, people. Let it rain B. Let it rain B. Just put B in. Just put B. Just put B. Okay, you don't have to. It's fine. I get it. You don't have to put any more B's in. All right, yes. Yes, now this does work because you're going to have 1 minus 200 over 400. That's 0.5. 1 minus 0.5 is 0.5. Okay. Okay. You know, on this test that we're doing on Wednesday, I'm going to put a question. I'm going to put a question that just says, what's your favorite unit for temperature? That's what I'm going to put. And you can put it, or you can put anything you want. But it's not about what you like. It's what you ought to do. Be good people. All right. Let's do a little more complicated stuff here, actually. All right, Carnot engine takes in heat from reservoir at 400 Kelvin. Yes. And discards heat to reservoir at 300 Kelvin. That's not amazing, but okay. If the engine does 12,000 joules of work per cycle, how much heat does it take in per cycle? All right, so now what we're doing here is we have our Carnot engine. We have some information about temperatures. We have some information of work being done. So use the relationships that you know and tell me what is the amount of heat being done. Okay. Yeah, some of you saying A. I like A. The reason why I like A is because it's correct. All right, so let's talk about it, right? This Carnot engine operates from 300 to 400 Kelvin, which means it has a efficiency of 25%. All right, so 25%. Well, the efficiency of a heat engine, right, is work over QH. If the efficiency is 0.25 and the work is 12,000, well, the denominator has to be 48,000. I gotta figure out why it's doing that streak thing. I don't know why it's doing that. But anyway, so the answer is A here. Excellent. Okay, give me a second here because Zoom is I'm not really happy with what Zoom's doing right now. So I'm gonna say don't save changes. Let me go back. Give me 1 minute here. No, the glove makes everything better. The glove, I mean, I feel better, feel a little more empowered, but I don't know. I hope it's not something wrong with it, you know. I mean, I'm doing something wrong clearly. So anyway, yeah. So give me a minute here because, well, thank you. My 120 students were making fun of me though. I was like, come on, people. I'm in charge of your grade. You gotta kiss my butt, man. Don't make fun of me. Not how that works. All right, let me get my slides back up because this is things got a little weird with Zoom here. So sorry, give me 1 second to find. No, that's not right. There we go. Physics 120. The last thermo lecture tier. So sad. We're leaving it behind. All right, here we go. Let's screen share this. I think I finally... Okay, so what is the efficiency of this heat engine? Let me know what you think. Is this the right question? It is. Okay. What is the efficiency of this heat engine? I knows what's up. Oh, I shouldn't say that. I was going to say A. It's A. It's A. Shouldn't have said that. I was going to say A. Okay. Well, you look at this and say, well, look, it says 300 and 600. The answer is B. Well, guess what? This isn't a Carnot cycle, is it? What are these processes here? A bunch of isobaric and isochronic processes. That's not Carnot cycle. No, 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 no. Yep. All right. Basically, all these questions are just a big trick. I'm just kidding, not a big trick. No, there is a lot of things to keep track of. I will admit, that's right. And when you see this, you got to keep a lot of things in mind, especially when we get to this point. You got to remember all the PV diagram stuff, all of the thermodynamic processes. You got to remember how to calculate work, all this stuff. So it's piling up here. And it's a lot to keep track of. And honestly, learning all this stuff in a month is rough. I don't envy your situation, but I nonetheless teach you. Okay, but yeah, this is not a Carnot cycle. You need to have adiabats and isotherms in a Carnot cycle, and these are neither of those. So that means the efficiency is at best 0.5 if you have a Carnot cycle. This is not a Carnot cycle, so the answer has to be A. Okay, the answer is not D or E. I don't even know why I have these options in there. I guess I have these options because if somebody says E, well, I guess I got to reach out to them because they're struggling. So, anyway. What's going on with this heat engine? What do you think about this? Is it a Carnot engine? Is it a less efficient engine? So when I say irreversible engine, translation, it's less than maximum efficiency, or it's impossible. What do we got in the chat here? What are we doing on time? Pretty good on time. A lot of C's. All right, well. Okay, remember efficiency is this, right? Efficiency is 1 minus these ratios, whether it's, you can have QC or QH here, it doesn't matter which one you have here. What is QC over QH? Well, QC is 2,000 and QH is 8,000. And so that ratio there is 0.75, right? So that's pretty crazy, right? Over here, though, this is 300 over 600, and that's 0.5. So this doesn't make any sense. We are not discarding enough heat. If this was a Carnot engine, we would be discarding 4,000 joules of energy. This is what I said, sorry, the 0.75 here, sorry, it's 0.25, and the efficiency is 0.75. And the efficiency based on the temperatures would be 0.5. So this is not possible because we're not expelling as much energy as the laws of thermodynamics require, right? So this doesn't work. The bottom number here, the 2,000, should be 4,000, and then the answer would be A. And if it's anything higher than 4,000, the answer is B. So isn't that something? It is. Very much something. Okay, well, let's see here. Let me just take a minute and look at what we're doing here. I want to see it. Do I take a break now or do I take a break later? Give me 1 second to look at the remainder slides and figure this out. Ooh. Okay, I will do this example, and then we'll take a break, and if you're bored, you can ponder the in-class example. I'll do it anyway. It's pretty straightforward stuff. This one's wild, though. This one's wild, all right? So gloves off for this one. Gloves off, because I'm not writing anything for this one. I wrote a bunch of stuff up for last year for this. So I'm going to show that to you. So let me bring up the screen share on my notes here, which would be located right nowhere, apparently. Oh my goodness. Today is the 14th, it is. All right, so we got to go through this very carefully. Very carefully. All right, we have 0.2 moles of a substance. It's a diatomic gas. Let's just say it's air. It undergoes a Carnot cycle between two temperature reservoirs that are given with a starting pressure. The PA that's mentioned here, this is pressure at point A, which point A is on the diagram here. The volume doubles during the isothermal expansion, which is step A to step B, and we need to figure out a lot of things here. Pressure and volume at all locations, and QW and delta T, QW and delta E thermal for each step and for the entire cycle, and we want to know what the efficiency is. Okay, so if we look down here at our process, okay, let's first look at the process. We have our A to B is the isothermal process where heat is added. B to C is the adiabatic process where the temperature drops and no heat is added. Process C to D is an isothermal process where heat is discarded. And then D back to A is an adiabatic process where the temperature goes back up with no heat transfer. Okay, there's a lot of pressure differences and temperature differences happening here. The left side of this goes through with different ideal gas law relationships and adiabatic relationships to figure out all the pressure and volumes at all the given steps. In step A, I'm given the pressure as basically 1 million Pascal. Okay, so be careful because this is a P subscript A, mean pressure at A, and the unit is Pascal, which is PA, but that's not a subscript, so not the best notation, but we have nothing better. Anyway, I use the ideal gas law to determine what the volume is going to be at that step. Now, I would use the hot reservoir temperature because we are on the ice. We're about to approach the isotherm and the temperature stays hot there. So I put in my moles, 0.2, put in my gas constant, 8.31. I put in my temperature, convert it to Kelvin, right? Pascal, and I get this volume here. Fantastic. Now, in step A to B, during the isotherm, the volume doubles. So I have that here. So when we get to point B, the volume doubles. I can use an ideal gas law proportion to figure out the new pressure. If the volume doubles, the pressure is cut in half. So I now have 500,000 Pascal. Great. Now we go to BC, because I want to figure out what's happening at C now. My volume can be determined based on the adiabatic relationship with temperature. So this equation, you should remember, the equation is, well, the equation is it's the V times T, and the V, the volume, has the gamma minus 1. So if I put that over to the temperature, I get a 1 minus gamma over 1 here. So I'm going to put these numbers in. I got my factor of 2 in here because we've doubled our volume. Put in my temperatures, and now my gamma value, because it's air, right? It's diatomic, and that's 1.4 for the gamma value. Okay. And so I put all that in and end up with a much higher volume of, well, not much higher, but 59.6 times 10 to the 4. And then I can use the ideal gas law to figure out the new pressure, which is somewhere kind of, you know, well, it's a little bit lower than what we had before. Wait a minute. Wait a minute. That doesn't make sense. Uh-oh. Okay, I guess I got to do some math here. Because my pressure, according to my diagram, continues to drop. So what did I do wrong here? Well, let me recalculate. I'm recalculating, by the way, this expression here. Because according to this, oh, it's a different exponent. That's totally legitimate. Sorry, that's fine. There's nothing wrong with that. Yeah, I missed the exponent. Yeah, the pressure's got to be lower, and it is. I just didn't see the 10 to the 5 there. All right, let's push on. Now we got our C values. Now we just got to get the D values, right? So we look at the adiabatic process, and I'm going to do pretty much the exact same thing. When we go from D to A, I know my volumes and temperatures and pressures at all the other points. So I'm going to use the same stuff I did previously, the adiabatic process. I'm going to use the relationship with temperature, and I get a new volume from that. And I'm going to get a new pressure from that. It's a little bit larger, but you notice not quite as big as the other one. The other one's a little bit higher. Okay, it doesn't seem like it's a lot higher in the diagram here, but according to the numbers, there's a pretty big difference, like a factor of 3, actually. So this B probably should be pushed up a bit more. Whatever. So that's all of part A. That's just working out all the state variables at the different states of the system. Then I want to work out the Q, W, and E thermal for each step. Now that's all first law of thermodynamics, and we just got to remember how we treat the first law in all these processes here. A to B is an isothermal process. Okay, so E thermal is 0. The QH is equal to the work that's being done. The work that's being done is given by this relationship that we've already determined, nRTH times ln of the ratio of velocities. And I get my QH, which is 576 joules. I go to BC, that's my adiabatic process. With adiabatic process, the work is equal to E thermal. Okay? So I take my difference in my temperatures here. Now when I go from B to C, just to be clear here, I'm dropping in temperature. Now this is a negative in front of the W here, but then I just incorporated that by subtracting the temperatures like this instead. So I just made everything positive. Anyway, the work being done in that process is 832. Let's move to CD. Same thing as A to B. It's an isothermal process. You go through the same steps. The volumes are different, right? Because we're going from a higher volume to a lower volume, so the natural logarithm is negative because of that. So we get a negative 346. And then we got our adiabatic process again, which happens to be identical to the BC step. In both cases, we're operating between the two temperature reservoirs, and so we get the exact same thing. We get a negative 832 joules here. So before we were working at a from B to C, we were going from a higher to a lower. Now we're going from lower to higher. And so you can see what the works are in each case. Q's are 0 in the adiabatic processes. In the isothermal processes, the work and the heat is the same. And and to get the efficiency, we just use our definition. It's a 40% efficient process. If we look at everything that's being done here, ultimately what's going on here, we're doing this much work, 832. We're putting in 576 and we're spitting out 346. So this is a 40% efficient process, apparently. 40% efficient process. Let me just double check that calculation there. You got it. All right. So the fact that we are putting in 576, we're doing a bunch of work, and we're expelling 346 means we have a 40% efficiency here. Okay, there was a lot going on in this problem. This is sort of like just threw everything into the pot here, right? It's like we're making a meal and we're just using everything in the refrigerator, pretty much. We got ideal gas law stuff here. We got thermodynamic process information. We got adiabatic process information. We look at expressions for thermal energy. We have the CV values were embedded into this, right? So there's efficiency in here. There's a million things going on in this problem. Now, on your homework, I'm going to give you a very similar problem. You're basically going to go through and do this again. Now, doing this problem is great for a lot of reasons because it involves so many things we've already done in this class. So it's a good exercise and just reviewing a lot of stuff. I mean, almost everything is in this problem, really. Let's talk about activity 1. This one's pretty straightforward. Carnot engine takes 2,000 joules of heat from a reservoir at 500 Kelvin. That's the QH. Does some work, yada, yada, yada. It discards some heat to a reservoir at 350 Kelvin. How much work does it do? How much heat is discarded? And what is the efficiency? Okay, so we got the magical relationship right here for Carnot engines. The ratio of the heats is equal to the ratio of the temperatures. And so that tells us exactly what our QC is here. Solving for QC yields a 1,400 joule amount. We subtract hot from cold to get the amount of work being done, which is 600 joules. And then we throw in our temperatures, which we can throw in the temperatures, we can throw in the heats, but we'll throw in the temperatures here, and we end up with a 30% efficiency. All right. Now, let's get to some new stuff. Not that new. Let's get to some abstraction. I guess that's the word I'm trying to use. Oh, not yet, I guess. Yeah, so the Carnot engine can be any kind of engine. It doesn't have to be heat. It can be a refrigerator. And if it's a refrigerator, the same relationships apply. The efficiency that we had for the refrigerator was QC over W, but we can algebraically manipulate that into temperatures as well using the same relationships. And what we have here is basically cold reservoir temperature divided by the difference between their temperatures, which would be related to their work, right? So this works too. This is what the Carnot refrigerator will do, and the efficiencies as they apply to those. Okay, 1 second. Scout, you gotta be quiet, Scout. All right, so we've been hinting at a lot of things when we talk about the second law of thermodynamics. And, having all these statements about what the second law of thermodynamics is, saying, you know, what heat engines can and can't do, what refrigerators can and can't do, statements of efficiency, you know, part of you starts to think, well, is there some kind of grand unifying theory in all of this that allows us to make really a single substantial, that's not a word, substantial statement that can encompass all different processes for the second law. And there is such a quantity, there is such a concept, and this is what we refer to in physics as entropy. Entropy is an attempt, okay, an attempt to quantify disorder. Now, we are not going to get into the details of entropy, unfortunately, because the details of entropy require us to go back to our kinetic theory of gases and start looking at things from a very fundamental standpoint, which we don't have the time to do. Furthermore, a proper analysis of entropy does require a sort of a sliver of quantum mechanics. And we don't cover quantum until the end of the class. Now, we could go back and revisit this concept. It's just not in the curriculum to do so. So unfortunately, we're going to just lightly touch on this process. We're going to look at some basic equations here, but not really go more beyond that. The idea with entropy is we're trying to measure the amount of disorder in a system. And what the second law of thermodynamics says is that processes ultimately tend to more entropy. They tend towards more randomness. Spontaneous processes. That's why when you drop a glass and it shatters, that creates a lot of disorder, right? You don't see processes where a bunch of shards of glass come together and then rise up into the air and you create a glass in your hand. That would violate this because you can't spontaneously create a bunch of order. You usually have to perform work to get that order there. Okay. So let's try to develop this idea a little more, actually. There is a mathematical way that we express this. So S is the symbol that we use for entropy. And so we are going to define a small amount of change in entropy as a ratio of how much heat transfer happens at a given temperature. Okay, so these are differentials here because we're imagining, you know, small little steps, for example. Now, this is our Physics 211 definition, by the way, of entropy. If we have a higher level of physics, we actually start to look at what we call microstates, right? Microstates, where we look at individual atoms and we ask ourselves, what are all the different configurations these atoms can have? And we look at all the microstates and we add up those microstates, and that reveals for us on a microscope. All right. We look at, you know, individual atoms and how they're affected by thermodynamic processes. We're going to keep this more general. Okay. We can integrate this, and that's what we typically do, to get this statement down here. The change in entropy in a process, reversible, okay, is an integral of dq over t. And so, again, this is all about energy transferred at a given temperature. Now, this may seem strange. It may seem disconnected to what you conceive as disorder, but physicists over time, this is what we have developed as the means to characterize disorder. We characterize disorder by what kind of heat transfer can be achieved at a given temperature. Imagine your temperature is extremely high and you transfer a small amount of heat. Well, the entropy of the system won't change very much. The amount of disorder in that system won't change too much. What if you have an enormous heat transfer at a very, very low temperature? That will produce very dramatic effects in your system, and that would produce probably a lot more disorder. So that's sort of the attempt that's being made to do this. All right, so anyway, it's all about this integral, though. Okay, and by the way, there's no special units for this quantity. It's joules per Kelvin. Joules per Kelvin. What is the change of entropy? There's a problem. What is the change of entropy for 1 kilogram of ice that is melted reversibly at 0 Celsius converted into water at 0 Celsius? Ooh, this looks good. So what's happening here? The change of entropy, melting ice and convert it to water. Well, here's what's cool about this. There's no temperature difference, right? There's no temperature difference. So that makes the integral pretty darn easy. Pretty darn easy. Let's look at it. So that integral becomes just a regular analytic statement. The t comes out of the integral, right? You're integrating from one state to the next dq. Well, that's just delta q. So this really, if you have an isothermal process, this is an isothermal process, then your entropy is always calculated in this following way, because you can take your temperature out of the integral. The heat transfer is not dependent on the temperature. So the change in Q is simply the latent heat of fusion for that kilogram there. So we got 1 kilogram times the latent heat of fusion. Realize that this is kilojoules per kilogram. So I put 10 to the 3 here to put in terms of joules. Divided by the temperature at 0, temperature is just 273. And we get basically 1,220 joules per Kelvin, or 2.11 times 10 to the 3 joules per Kelvin. And that is the change in entropy. So the entropy of the system increased in this process here. We broke apart molecular bonds, and that's how we're characterizing how the disorder of the system took place. Now, what's nice about this is a reversible process, and you could slowly extract the same amount of heat out, and you could lower the entropy of this. But ultimately, the change in entropy for the cyclic process is 0. If you have any kind of cyclic process, the delta S is at best 0. And that's another statement. Well, that's kind of what we're saying about the second law of thermodynamics here, is that a Carnot cycle is a delta S of 0. And any other process has a delta S that's positive, and impossible processes cannot have a delta S that is less than 0. An individual step, yes, can have a negative entropy, but a cyclic process cannot be negative. That's, our more substantial or more comprehensive statement of the second law. Okay. Where is my slides? Here it is. Here it is. All right, let's do another example here. A kilogram of water at 0 Celsius is heated to 100 Celsius. Compute its change of entropy. Assume that the specific heat of water is constant over this temperature range. Well, this is different. This is different because now we do have a temperature change. So that means we're going to have to rewrite our dq in terms of a temperature difference. Now, we're doing specific heat here, though. So the energy required is mc delta t. So we replace our dq with mc dt. Nice. Easy integral, right? Turns into a logarithm. mc times the logarithm of the final minus the initial, well, final over the initial if it's logarithm. So we'll put our numbers in here. We got a kilogram. We got our specific heat for water. We got our final initial temperatures. And we end up with this thing right here. We get an increase in entropy, very similar to the last one, by the way. A little bit more though. And that's a coincidence. There's no reason why these are same. It just happens to do with with what the specific heats are and latent heats, things like that. Okay. All right. Question for you here. Ideal gas is taken around the cycle shown in this PV diagram from A to C to B. A, we're going to the right, we're going up, we're going down. Which of the processes in this cycle could be reversible? Ooh, what does that smell? Smell pancakes. Smell pancakes. I'm not eating a pancake this late though. Ugh. I'm gonna be going to bed at 5 p.m. The answer is B. The adiabatic process is a reversible process here. Because Q is equal to 0 in this process, there is no change in entropy in this. Now, there will be change of entropies going from B to A and A to C, of course. There's, energy is taken out in the B to C process. Energy is put in the AC process. The temperature changing in those processes. They're not as easy to calculate, to be honest. They're a little bit more complicated, but the adiabatic process is very straightforward. Excellent. All right. For the Carnot example that we did, the activity one right after the break, we want to figure out what the total entropy changes during that cycle. So let's look at that. So that was the one where we had, 350 and 500, I believe. That were the temperatures that we're working with. Let's go down more here. Okay. So for the Carnot example, that was example 1. Oh yeah, it was. Okay, sorry. So in the Carnot process, we have 4 processes in our cycle. So for each of the 4 processes, we can have a statement. Now the adiabatics are really simple, right? Because there's no change in the heat. There's no heat added or taken away. Delta Q is 0. Delta S, therefore, is 0. In the isothermal process, we do have heat transfer. The heat transfer here is our QH in the first step divided by the TH. That's equal to 4 joules per Kelvin. In the isothermal process, that was step 3, we have 1400 joules removed, so we got to put a negative there, at a lower temperature, but it does turn out to be the same ratio. This is how we know. This is one way we know that we are dealing with a Carnot process, because the isothermal processes ultimately result in no change in entropy. So the whole process has no change in entropy at all. Okay? And that's how we're able to calculate that. Now, if we did not have a Carnot process, if we had a less efficient process, then what would happen is, well, step 1 would be larger than step 3, and we would end up with a net positive. Okay? So this really is our sort of final second law of thermodynamics statement. It requires a lot of context, and that's why it took so long for us to get to this point to state this. I couldn't tell you this to begin with because we'd have to look at, well, what's entropy? Okay, what's a reversible process? What's this? What's this? So it took a long time to lead up to this point, and that's why, and this is sort of a traditional pedagogical, let's say that word right, pedagogical, in terms of teaching, you don't just throw this statement out to begin with, because there's a lot that cannot be appreciated about the statement. So this process here, the statement is, no process is possible in which the total entropy decreases when all systems taken part in the process are included. Now, no process does total entropy decrease. At best, it can be 0. But even if it's 0, you'd have to actually look at what's happening in the environment. Now, there may be no change in the environment in terms of reversible processes, but if you look at generally what it takes to produce that cycle, you do notice that there is some entropy there. So, and there's a more ridiculous statement that people use, and that's this. The entropy of the universe always increases. That's a weird statement. But when you say the universe, you automatically are talking about a system and its environment. And in the universe, every single process that takes place in the universe increases the entropy of the universe. Okay, weird statement. Weird statement, right? So, yeah, I mean, look at this process down here. This is kind of a neat thing. You drop in some, ink into this, and what happens is over time, it gets sort of chaotic and it spreads throughout. Well, the ink was concentrated in a small area, and naturally, you have a process which the liquid becomes homogeneous. Well, that's an increase in entropy, though. Okay, anyway. One more example, and we're going to be done here. So let's look at that example. All right, so suppose we have a kilogram of water at 100 Celsius is placed in thermal contact with a kilogram of water at 0 Celsius. What's the total change in entropy, assuming that the specific heat of water is constant over this temperature range? Well, guess what? We know what's going to happen here, don't we? We know that we're going to end up with 2 kilograms of water at 50 C. So you think about that and you say, well, okay, we get into an equilibrium. We get 2 kilograms of water at 50 C. Great. From an entropy standpoint, not as simple though, all right? So clearly, the 100 C is dropping down to 50, and the 0 is dropping up. Dropping up, okay. Going up to 50. It's been a long day. All right, so we got our statement for entropy, right? We do have a variable temperature. We're going to use specific heat, though, for this, so we know this expression. The hot water drops 50 C. Right, but we're comparing that to a higher initial temperature. So we lose energy, and we drop to 603 joules per Kelvin, negative, right? Now, the same temperature change occurs, but we start from a lower temperature going up to a higher temperature. And if you work out those details there, again, final minus initial, we have a higher amount of entropy there, 705 joules per Kelvin. The difference between these is around 102. So ultimately, yeah, there's an equilibrium in this process. But ultimately what happens is when you compare the hotter to the colder things, you do end up with a net increase in entropy for this system here. So anyway. Okay, now, like I said, I'm going to stop my video. It's probably 10,000 megabytes.